Welcome to our afternoon session for talks, or invited talks. Our first talk is Andreas Griewank from Tech in Ecuador, and he will be talking about high-dimensional integration of kinks and jumps, smoothing by pre-integration.
Okay, thank you very much. Buenas tardes. Thanks very much for the invitation to speak here, although I don't really, I think, belong to the community. Directly, this is work that I did a few years ago together with my then PhD student Herman Leove and with the two co-authors Francis Kuo and Ian Sloan, which are both, who are both very, very well known in the QMC community. And QMC for me means quasi-Monte Carlo, not quantum Monte Carlo. So there is a bit of a confusion in the terminology. Well, for the last 3.5 years I've been working at Tech. So this is a picture. There's some old hacienda parts. It's high up in the mountains at 2,100, well, not compared to Bogota. And here you see some new buildings which unfortunately mostly were badly constructed and can't be used. Nevertheless, we tried to develop a university there, which was basically, it's halfway between Quito and Colombia. And it was basically the idea of Korea, which, like all other projects of Korea, are not necessarily very popular right now. So here is the glossary introduction motivation. So we're trying to get rid or deal with kinks and jumps in the integrand of a high-dimensional integral, and that is done by pre-integration and can be viewed as a projection on function space. And the question is, how well can the resulting function be integrated by quasi-Monte Carlo or by simple straightforward Monte Carlo methods? And here when I say Monte Carlo, I don't mean Markov chain Monte Carlo, but the original Monte Carlo, which requires you to generate a sequence of sample points with the required probability distribution. Then, well, there are some numerical examples from mathematics of finance, option pricing, conclusion and outlook. And this morning I added an extra one. We actually also did some work on quantum field theory, on lattice systems. So if I still have time, I will just show the numerical results. So high-dimensional quadrature, we have an integrand f of x and a probability density rho of x, and we try to integrate over a space, which for a technical reason I write as R1 plus d, where d is something 50 or bigger, which until not that long ago was considered to be almost undoable. So the Monte Carlo approach is to generate a sequence of sample points which have to have the right probability density distribution, and then we take the average of the first n function values and call that the quadrature Qn of f, and hopefully it's close to the actual exact integral. Now it is very well known that under very reasonable, essentially L2 integrability, you can show that the error between the quadrature and the real integral declines like 1 over square root n, where the n is the number of sample points. So that's not very fast. The good news is the dimension doesn't show up. So that's the main reason, I think, why quasi-Monte Carlo became so popular and is widely used. Now, 1 over square root n is not terribly fast, and the quasi-Monte Carlo, the holy grail is more or less to replace this 1 over square root n by 1 over n. It doesn't quite work. There is usually a slack factor delta greater or equal to 0, so the decline is 1 over n to the 1 minus delta. And as you can imagine, there is a constant sitting there, and that constant usually grows pretty rapidly as you push the delta down to 0. And it all depends, of course, on the method and on the smoothness of the function. Not just the order of differentiability, but it has to be in certain Sobolev space, or space is better in certain tensor spaces. Now, in many cases, the integrand is not directly smooth enough. So the simplest case is you just take the maximum of the value at the end of the simulation period minus a strike price k and 0. So if you're below this strike price case, you get nothing. Otherwise, you get the difference. And because of this max value, the integrand does not lie in any mixed derivative function space, which you need for quasi-Monte Carlo to work well. And the same kind of condition pops up when you use so-called sparse grid methods. So here's a very, very simple example. We just assume the total dimension is 2. We assume the function, the integrand, the original integrand is phi of xy is equal e to the x minus y. And we want to integrate f of xy, which is the maximum of this, and 0. Now, one property that this function has is that it's strictly monotonically growing with respect to x. So when y is positive, we have exactly one root. When y is negative, we have no roots at all. And when there is a root, we can replace this the integration with respect to x and some Gauss type distribution. We can simply cut off the integration at y is equal log y, and then we get this expression which we have to integrate with respect to y. So we first integrate with respect to x, that gives us this, and then we integrate with respect to y. And that's a perfectly smooth function in y, so we can use our quasi-Monte Carlo sparse grid method or whatever. And of course, this is nothing terribly new. We did this about 3 years ago, and the paper occurred at the beginning of last year. So these are, as I said, there's a whole community of people doing quasi-Monte Carlo and annual conferences and whatnot. So the general setting is we have 1 plus d variable. The first one is called x0. And that's the one we're going to throw out because it generates the to eliminate the non-smoothness. And we assume that the probability density is multiplicative in the various coordinates. Or at least we can pull out the part for the first variable x0. And then we have f of x0 comma x is either the maximum of 0 and some smooth integrand theta. And this can be written simply as theta x comma x times the indicator function of theta x naught comma x. So indicator, of course, is just a characteristic function. When we're non-negative, it's 1, otherwise it's 0. So this gives you an integrand that's still Lipschitz continuous, but not differentiable. But the people also use so-called binary option, where the return is discontinuous relative to the strike price. So what we allow here is that the theta in the indicator argument is replaced by an arbitrary function phi of x naught comma x, arbitrary but also sufficiently smooth. So we assume that both theta and phi are r times continuously differentiable. Moreover, we assume that the derivative of the switching function with respect to x naught is strictly positive. And then as we push x0 to infinity, the function of the value of phi goes to plus infinity. And that means this strict monotonicity, strong monotonicity, is that there is a boundary function that is for each fixed x, we can find an x naught, a unique x naught where phi x naught x vanishes, or phi may not have root at all, in which case we have the empty set and the supremum is as usually set to minus infinity. So we have this boundary function psi is extended continuous from Rd. Rd are the remaining variables to minus infinity union R. Now wherever the root is finite, so this function psi is finite, these guys belong to an open set, and on this open set the function psi is actually also R times differentiable, just as a consequence of the implicit function theorem. And the complement of points where we may have trouble because psi runs off to minus infinity is represented as u plus. Now, by Fubini's theorem, we know that in order to evaluate the original integral in d plus 1 variable, we can first integrate with respect to the 0th variable and then integrate what we get by the remaining, with respect to the remaining d variables. And the first integration we write as p psi of theta, which is the integral of minus infinity plus infinity of this cut function f of x comma x times rho of x0. And that's the same as the integral from psi of x, which may be minus infinity, but it also may be finite, over the smooth integrand theta and the also smoothly assumed probability density function rho. And then the idea is, if we somehow can do this projection or this reduction exactly, in some of these math of finance problems you can do it symbolically. In other cases, one-dimensional integration you can do by adaptations of Gaussian quadrature practically to any accuracy with a reasonable effort. And then the remaining function is integrated by some kind of sampling on the space Rd. So what are the desirable properties? Firstly, as we can show quite easily, the variance of this projected function is equal to the variance of the original functions times 1 minus the so-called Sobolev exponent of x0, which measured how strong the function f depends on x0. We get continuous differentiability under the assumption that theta and phi are R times differentiable. The same is true for the projected function. Now, of course, for efficient numerical integration, just point-wise differentiability is not good enough because you could be awfully oscillatory. So you also need boundedness in a suitable Sobolev norm of total order here, R here. And even better is, I said there are subspaces of the Sobolev spaces. There are so-called tensor spaces. And if the function belongs to that, you can prove this 1 over n convergence of quasi-Monte Carlo. We also would like to have some bound of this projection in a suitable norm, but we haven't been able to come up with that. So the variance reduction is very simple. We're in of course we assume we are in L2. So you can write your function f of x as the sum of 2 to the d plus 1 ANOVA terms, 1 for each subset of the u of the indices 0 to d. And these contributions f of u are all orthogonal, and the hope is that the mixed ones that have lots of depend on lots of variables are comparatively small, and the ones that depend on one or only a few variables are dominate this expansion. Now, if we do apply this integration, pre-integration to this f of x, because of the orthogonality of these terms, one can find that the projection of all the terms where u is an element in the index set is simply 0. So what we remain with are the terms, and they're just identically reproduced for which x0 is not in the variable set. And then we find that the variance of the function as it was originally is the sum of all the variances of the ANOVA terms that do not depend on u plus the guys that do on x0 on 0 plus the guys that do depend on u. And these, as we've seen here, they're integrated out, so the variance is reduced from the sum to this remaining part, and that benefits both Markov, both Monte Carlo as well as quasi-Monte Carlo. Now the smoothness is a little bit tricky because, well, we had this function p psi of theta. So if we differentiate in this form, if we differentiate this with respect to any component of the remaining variables, say xk, we get two terms. Firstly, the term by differentiating the integrand and keeping the integral, and secondly, the term by substituting the boundary into the argument for x0 and then multiplying by the derivative of psi with respect to the corresponding variable xk. So this is what you get. The kth partial derivative of the projected function is the projection of the kth partial derivative of the smooth part of the integrand plus the integrand evaluated at the boundary point plus the derivative of the boundary point with respect to, actually this is actually supposed to be phi 2. Phi of psi of x. And by the implicit function theorem we can write this thing down explicitly, and in the denominator we have this partial derivative with respect to x0, which we have assumed to be strictly positive. That's this strong monotonicity assumption. And if you keep applying, differentiating repeatedly, you get a horrible expression of this form, where basically you have this derivative d0 to certain powers in the denominator. You also get certain derivatives of the probability density and some horrible stuff here. And the key assumption in order to prove what we're trying to prove, namely that the projected function p psi is smooth, is we have to show that as we approach the boundary of this open set where psi is finite, all these terms go to 0. And so the boundary of this regular set u can be pretty horrible. Here's a little example which is rigged up so that it's m times differentiable. It's certainly monotonic with respect to x0, so it satisfies that assumption, and we can write down x0 as the m times the log of the positive part of x plus the log of the positive part of sine of 1 over x plus, and this generates an infinite sequence of subintervals on the reduced domain, and we have to show the differentiability across the boundary. So this is the regular domain, this is the complement. Here's the picture. So this is here is the boundary where psi is positive, so it's finite, there's a root. Here psi runs off to -infinity. Here the function has no root, phi has no root with respect to x0. Then we reach another lobe here and so forth, and there are countably many of them. And the difficulty in here, it's perfectly clear that the pre-integrated function is smooth. In here too, and we have to show that they fit together on these boundaries, including the ones where we have a countable set of subsurfaces. And by some little technical argument you can actually show if you have a function that's r times differentiable on an open set, such that with mixed derivative of total order up to r, and if you can show that as x approaches the boundary point of u, that then all these derivatives vanish, then you can set the function to 0 on the complement of u, and all the derivatives to 0 too, and you get a CR function. And that's sort of the technical back part of proving this following proposition. So provided all these h's go to 0, then if theta and phi are r times differentiable and rho 0 is r minus 1 times differentiable, this pre-integrated function will be r times differentiable. And then, well, the question is how you make a statement about this horrible mess. And my ex-PhD student came up with this representation, a sufficient condition. If you can express all these as the product of a function in x naught that goes to 0, as e naught as x0 goes to minus infinity, and some reasonably locally bounded and p-integrable function in the other variables, then this condition is satisfied. So not only do all these derivatives exist, but as I said, we want to show also that these derivatives are integrable, and the statement is that if we have the differentiability of order r, then we also in this space, in this Sobolev space, where all mixed derivatives are integrable up to total order r. And this means that if theta is in this Sobolev space with 1 plus d variables, then the projection is in the same Sobolev space with this n should be d. I'm sorry. So, how much time do I have left?
10 minutes.
5 minutes?
Yeah, 5.
What did you say?
I said 10, but it's...
No, 10 is perfect. So this is a binary arithmetic option. Why is it binary? Because this is the value at the end of the simulation period, and we multiply it by the indicator function of the difference between the value minus k, which means the return jumps as the value crosses the strike price k, and the probability density distribution is the covariance matrix for the Brownian motion over the sequence of 256 or 255 time intervals, and the corresponding covariance matrix is simply min ti tj. So, as Juan explained in his talk, one can improve things usually by doing a principal component analysis, in this case of this covariance matrix, and if we do the eigenvalue decomposition, that's called PCA, and the lambdas are the eigenvalues, and the eta 1s to eta d's are the corresponding eigenvectors, and then we can rewrite the integration as essentially an integration over a Gaussian distribution. So here are the numerical results. Asian option means not binary, so we are still continuous but not differentiable. We take two sets of sequences, the one of 2 to the 10 with 2 to the 10 points, sample points 1, 2 to the 12, 1, 2 to the 14. This is the root mean square error produced by classical Monte Carlo. This is the root mean square error produced by quasi Monte Carlo, and you see that here the convergence rate is approximately 1 over n, whereas up here it's approximately 1 over square root n. If you do this pre-smoothing, and I said the pre-smoothing reduces the variance, that also helps a lot standard Monte Carlo. So the slope is still the same, but we gain 1.5 orders of magnitude. And then if we pre-smooth and apply quasi Monte Carlo, we have again the rate of n to the minus 1, and are about 3 orders of magnitude better than the plain vanilla Monte Carlo on the original problem. So the Asian option is the one that has not only a kink, but it has a jump. And you see both Monte Carlo and quasi-Monte Carlo have significantly larger errors. Also, the slope for the quasi-Monte Carlo is only minus 0.6, not the -1 we're looking for. If we pre-smooth, it helps again Monte Carlo quite a bit, and it really works well for the quasi-Monte Carlo, which essentially gets the same error as in the continuous case. So this is the discontinuous case. Well, let's jump that. So conclusion and outlook. Smooth, simple kinks or jumps. So simple means along this one distinguished variable there is only one root. In one variable can be eliminated by pre-integration, and this operator we call p psi. The variance is reduced by the Sobolev index of the special variable, yielding benefits for Monte Carlo and quasi-Monte Carlo. It maintains the differentiability, this pre-integration in the mathematical sense and mathematical integrability under certain fairly strong assumptions. And the strong assumption is basically that the distributions die away and their derivatives pretty rapidly as we go to infinity. Now the challenge is basically is what to do. We thought a bit about that if you don't just have one hypersurface of singularity, but if you have several of them, so you can have intersecting kinks. So just a few more slides on the different application, which may be closer to the heart of some of you guys. So basically my student did this work on lattice integration. Here's the action function, which the partition function. We have the harmonic oscillator when this potential here is just quadratic with a positive coefficient, and we have anharmonic if we allow for a negative coefficient here and a fourth order term. Then we can write the lattice action after discretization on a uniform grid in this cyclical fashion with certain numbers on the diagonal, which reflect the second order term. And the covariance matrix is a covariance matrix if this lambda, the fourth order term, is 0, which is the nice case. And we want to compute observables for this harmonic oscillator or for this anharmonic oscillator, and of course we want to do this with quasi-Monte Carlo. Here are the observables that were used in the experiments. Here you see for the expected value x squared of the harmonic oscillator, we get the Monte Carlo, Markov chain Monte Carlo are these slopes, these lines with a slope of about a half, which correspond, because of course we use log-log term, to 1 over square root n. And if you do quasi-Monte Carlo with a certain random shift, you get the holy grail, the desired decline by 1 over n. So here is another observable which was on the slide, but I can't fully interpret it. D is 100, so we go over 100 steps in the lattice. And here we see that for the Monte Carlo method, the rate of decline is minus 0.5, as was to be expected. For another observable, for x squared, the second moment, we get a similar picture, also decline with minus 0.52. Now what does the QMC do here? Empirically, for all the cases, it generates an exponent of about minus 3/4. And we, and I don't think anybody else, has actually been able to demonstrate that. But still, that's a pretty good gain compared to minus 1/2.
have a question.
Yes.
Two questions. One, is it this exponent? The exponent that you get, like in the standard deviation, how it goes with the number of samples, is it observable, is it dependent?
Well, it's the anamorphic.
Can you repeat the question, please?
Well, I think why this reduction in the exponent?
No.
No.
We are looking at like the expectation value over x squared. What if you look at another observable, v squared?
Well, I mean there's x4, x2, E0 was this funny guy. I don't know why this was chosen.
Okay.
But the big thing is, the big difference is between the harmonic and the unharmonic case. In the harmonic case, everything essentially reduces to Gaussian densities, and then the thing works very well. But in the unharmonic case, you have to mix the observable and the density function and do certain preconditions to make it still work, and that seems to create this loss to an exponent of -3/4.
So what happens if you have a many-body system?
And what?
A many-body system.
Oh, I don't know. We haven't done that. Okay, thanks for your attention and still being here at late Friday afternoon. Where's the...
Thank you. Any more questions?
Didn't look like it.
Okay. Thank
So
you.
what about like so you have a continuous system that you have discretized.
You had a lot of?
You have a continuous system that you have discretized. Could you apply this directly to like spin-based models?
I don't know. This is not my main line of work. And I depend a lot on the student, and as far as I know, we were the first to apply this to problems from quantum field theory. So on all the other ones, I don't know whether anybody's done it yet. I mean, parts of your community that the concept of quasi Monte Carlo is not known, is it? Or you never heard about it? Well, that's amazing. Because if you Google quasi Monte Carlo, so the key thing is that you do not select the points with a uniform distributed or somehow according to the row density distributed sample sequence, but you construct sample sequences basically by number theory in a very, very subtle fashion, and then you can show that the error between the quadrature and the real thing is the product of something that depends on this sample sequence. It's called the discrepancy, low discrepancy, which means it covers the whole space very nicely, and the Krauss-Lofgar norm or something of the integrand. And if this norm is bounded, which it isn't always, certainly not when you have kinks and jumps, then you have essentially this linear 1/n times a constant depending on the function. So as I said, Ian Sloan is one of, if you want to look things up, Ian Sloan is one of the big guys in the field and has given any number of survey talks, and I'm just a sort of a part-time participant.
All right. Thank you, Andreas.